Welcome back, everybody. Thanks for being here. So, we have no more quizzes. Is that good news?
Yeah. What are the answers to that?
Good questions. Okay, the assumed, answer one, the assumed structure of the residual covariance matrix in MANOVA is?
Not a clue.
A? No.
It's C.
Unstructured. MANOVA estimates everything.
Can I get one back?
MANOVA. No. The assumed structure of the residual covariance matrix in the repeated measures ANOVA is? Compound symmetry. Exactly. The assumed structure of the residual covariance matrix in multi-level models with a random intercept is? Compound symmetry. And finally, mixed models are said to blank. What's that? Consume. Subsume the classical methods of repeated measures, ANOVA and MANOVA. So the purpose of that was kind of the purpose of the last lecture, and it's sort of a key thing with it. So did that help? Or
Yes, thank you.
yeah. Questions on it? No? What's that?
You guys, if I got undressed.
Oh, no. No. So why are the quizzes hard? Let me ask that to you. Yeah, I appreciate the honesty. That's it. Okay, cool. Would other people second that? Because like studying for this could have been looking at the slides last time, right? Could have been like that. That could be the. I had chapters assigned or whatever else. But
I'm not looking at the things that you're asking.
Not looking at the things.
I'm not like really thinking. Okay, I'm really going to get this down, and then the things that you ask are not the things that I was like. This is what I remember.
What do you remember from last time? Let me ask you that. Since you're, thank you for volunteering. I appreciate that. Not to pick on you.
Now I have to come up with everything.
No, it's okay. Just any. Never mind.
Well, I was
I
trying
can
to
drop
remember, it. You know, it's like what the spherosity was, and compound symmetry, and when it's used. And I'm not going to say that I remember. Like,
Oh yeah. No, there's a lot to it. Yeah.
But for instance, I, for whatever the reason, was pretty sure that I had numbers 1 and 3 right, and I had them completely opposite.
Backwards. Yep. Fair enough. Yeah.
I just took last week's quiz, right?
Yeah.
I like the question because there's more of an application of what's wrong with doing listwise. Sounds more of that.
I remember last week.
It wasn't necessarily like a term,
Uh-huh.
right? But it was more just like, how would this be applied? Like, why not do this? So I kind of like that question because that's more in reality when I sit down. I'm not going to have the textbook definition of this unless it's for I can teach this position. But like understanding when to use it, what it will do if you do use it. I kind of like that wording in these questions because it was like, oh, that's what I took away from this.
Okay.
It's bad if you say listwise for these reasons.
Okay.
I second that.
Okay. So more how you use it rather than the terms itself. Okay. So I guess I'm kind of torn. Like I feel like the terms are important, right? Because you can't describe the analyses without the terms.
That's why it's hard.
No, I agree. I guess in trying to teach this class, it's a challenge. Don't get me wrong, right? And it's a challenge to learn it. So I'm trying to see how we could be more effective. I actually looked at the quizzes as a way to try to give you motivation to do studying. But if it's not working, what would motivate you to do more studying or otherwise look at the material from before to do more? You know, the thing is, you learn how to do models. There's plenty of jobs because there's a lot of people who don't know how to do them.
I think that there was more intersection between the homework and the lecture. I feel like I take away from lecture your R stuff and then kind of muddle through the homework. But if there was more.
Let's see, like the homework. I'm doing things with homework I'm probably not comfortable with entirely because I'm literally ripping off lecture. Like there are some homeworks that were verbatim with it. And when I was switched a little bit, you're used to verbatim and it was not as it. So it's like the layer of learning is not as high up as I wanted it to be for it. So I understand where you're coming from. Like if I can integrate homework from R, but I feel like it's like homework is lecture at this point. Like this lecture here is going to lead directly into homework, right? So I think how many hours do you spend reading about class out of class every week? Let me just ask. Be honest. It's okay if the answer is 0. If it's 0 inflated, it's fine too. I want to know because this is the point of the quiz. Because you can't learn this in lecture only. It takes effort and time, and the homework at least makes you spend more time on it. But that's it. So how many hours do you spend out of class reading?
Does reading include going back through your slides?
I'll go with that.
Because that is much easier to understand than reading articles, which generally use different terminology than what we've had in lecture,
Right.
and therefore are just very frustrating.
Oh, I understand that, but that's the world that we live in.
Right.
I can't go and make everybody write something in a uniform format, right? So I understand that, but it's like a pragmatic point of view. Like, how can you do this in the real world without having a taste of the real world as we're going forward, right? So I get it, but yeah, how many hours? Let me ask. With lecture slides, it's kind of.
I have no shame. I'm leaving academia after this.
Yeah.
I don't.
Okay.
Reading.
Okay, that's fair. I appreciate it. No, I'm just listening because I want to know. There's clearly something going on with the quiz, and I want to know what I'm tapping into. Like, if you're not going to, if this is the culture here, it takes a while to change. I get it, and no matter what I do, it won't change, right? It's the only way I can do it. But is there something I can do to be more effective at getting you to work more to do this? I think is the question. Yeah.
I hope I don't throw anyone under the bus with data across in the future. But honestly, the quizzes, percentage-wise, just doing the stats.
Mm-hmm.
The quizzes aren't enough to have me an incentive to do it.
Fair enough. No, I think that's good, and I think that's it. I don't want it to be punitive because I get it. Every week you may not have the time to devote. You know, it cycles, right? But on average, you want to make it happen. Fair enough. That makes sense. If that's a trade you're willing to make, that's your choice, and I get it. So, I just know I walk in with it, and I feel like the mood of the class is just so distraught. And actually, that's the reason, apart from teaching ratings. Actually, I want you to be honest in your ratings, but I gave you the quiz now because if you know there's not going to be one next week, right? There's not going to be one, so you don't. There's nothing tying you to points to being here. I don't want you to be here if you don't want to be here. It's not a big deal, but it's more the quiz was trying to incentivize a little bit more purposeful type of work, but I don't feel like it's doing that. Yeah.
I was going to respond to your reading. I think it varies greatly for me from week to week, depending on what the topic is, what the readings are, and what my life looks like.
I completely agree. Yeah.
And
Yeah.
so there are some weeks when, admittedly, I didn't read any of what you had down, and there are some weeks when I have read, but it's been less motivating for me because although it is the real world,
It sucks.
I really didn't have a clue what it was talking about. I didn't know what I would get from it, and by the end of what I was trying to read, I thought he could ask me a number of
Anything.
questions
Yeah.
on the quiz.
Yeah.
I don't think I could answer them, so I'm not quite sure what my time spent.
That's a good point.
Whereas, not that I wanted extra homework. That's not what I'm asking.
No, I
for.
get it. Believe me, I don't want to give it to you.
It might have been, I don't know, useful to be like, tell me about, X
Mhm.
from, that came from the reading, which would get me to go, okay, what is the reading?
That's a good
tell
point.
me
I can
about
ask a
this?
better question like
It
that.
just,
Yeah.
it seems, I know it's not random what you're pulling out of the air for the quizzes,
Mhm.
but it feels that way
Okay.
because I don't think I have a good sense of priorities.
Fair
What's
enough.
important. I mean, including like on the quiz.
There are a lot of slides last week, and there's a lot of terms and a lot of
Well, there are.
the
And like,
matrices start flying around. And yeah, I
you
get
asked
it.
for the 3 phases of multiple imputation. I was like, I know exactly what to do, but I don't remember what he called them or the readings called them.
Ah, right.
So I'm just going to describe things that happen.
I hear you. I hear you. Yeah, I think that may be a little overly precise. Okay. Well, I'll continue to try to adapt. It's Pearl, please.
My takeaway is I'm always when I'm kind of reviewing the PowerPoints and also I did not finish on reading either.
Fair enough. Yeah.
But my takeaway is, for example, if I what I want to apply, just how much I can apply.
Right.
To my take. I don't know. For example, if we can really examine one good example, not only about explaining about methods, but how they kind of build model and also like research questions. And then lead to the model and then to the analysis, the data.
Oh, I hear you. Yeah, I try to. That's what I try to do in lecture. Maybe I'm not hitting that point, but I think, I get what you're saying. Yes. Tying it better to research questions and so forth. Okay. Anybody else want to add to it?
For me, personally, the biggest motivation for me to read is so that I come to class prepared, so I can actually understand what you're talking in lectures.
Fantastic.
And then after the lecture, it feels like that part of the motivation is gone.
That makes sense. Yeah.
It was harder for me to go back to reading, and also for me to understand what you're talking in before coming to class.
Uh-huh.
And in my mind, I felt like I've done my part of the reading for the.
That makes sense, and that's totally legit. Like again, like I get the readings are hit or miss, but yes, reading the slides are fine. You know, that's at least a step in the right direction. So, but yeah, I hear you. And actually, on that note, I'd like to write a multivariate book. Here's the funny thing about books. Like my wife is teaching from a book right now that she spent 5 years on. She's having the same problem getting people to read, and it's her writing, and it's also not synced in, right? And so it's like, how do we bring about this in a place where we can get more effort from it? So, all right. Well, I apologize for the tense nature of the quizzes. I can tell you that much. I don't like to see you struggle. I'm not trying to play got you. I don't want that to happen. What I'm motivated by is to try to get you to provide work in the class in a reasonable way, understanding that you do have other classes and a life outside of here and everything else. And so how do we work together to make that happen? It's tough, I think. So anything you can do to suggest it, you know, you can write something down on an anonymous piece of paper. I'll take it. I'll listen. It's interesting. Our teaching rating forms don't actually have any boxes for you to write your opinion about. Like if your opinion doesn't fit with a 1 through 5, then we don't want it. But I do. I want to hear it because I don't like walking in. I'm tired of walking in here with quizzes and having it not go well and not knowing what I can do to make it better. Ginger.
For the quiz, I want to say sometimes I think the quiz for me is item with diff because I don't know the meaning of the words. I think it's my fault.
Fair enough. Yeah, it's tough, especially if you're an English language learner or a second language or third or fourth language, however many you learn, and English is later on the.
But I think it's my fault. I don't know.
Well, I know that's a tough thing. I understand that's the thing. Like I'd love to not give quizzes. I think I started giving quizzes actually with you guys, your cohort that came in. So these are the people who. No, I'm just kidding. I think they were here before you. No, it was because it was I didn't feel like a lot of people were putting any time in outside of class, and then I'd give out a homework that would be a fixed form homework, and they would do it an hour before it was due. It handed in, and that was it. And so it's like I feel like you can't learn statistics without doing them. And so maybe homework is frustrating is to get you at least do them more. So I feel like I'm winning on that note. Winning. I'm trying to get you to learn, right?
But it clicks, or at least for me.
It starts. It sucks. It sucks.
Clicks.
Yes. Yeah, I wish it could be more friendly. Like if you get it right, all of a sudden you get like $10, right? It's like a slot machine. Wouldn't that be better? No. Anyway, I appreciate your comments. I will, if you have other things to say, again, say them anonymously to protect yourself. You don't. I try to protect you, but you're welcome to double blind it, whatever, type them up. Submit a thing in my mailbox. You know where you can find it. I would just like to make this a better experience for those who come next. It's too late for you people. Just kidding. Just kidding. It's not too late for you, but you know the semester's almost over. I care very much about teaching. It's a very important part of my job. I also care that when I see you on the other side of this, if I'm on your committees or if I'm working with you on research and you come in and I say, hey, remember that Manova thing that we did, and you're like, I have no idea about that. Not cool, right? So that's also where we're working with, is trying to bring up the practice here. So, okay, there, I've had it.
Is that all on tape?
Yeah, it is. I'm recording it. Yeah, I hope that's you can hear it. Anybody else can hear it. I mean, yeah, let's. I don't know that I don't need to hide anything, right? I mean, it is what it is, right? So, okay. All right. It's interesting. I'll add one other thing to that. You know, as a professor, just like everybody in the class, we all have the time command, life, and whatever else is going on. Just like if you taught in schools, you know how hard it is to prep and do whatever else. It's just like the professor job. I feel like this is one of the first semesters I've really been diligent about hitting all the milestones I said I would hit. Like we had 6 homeworks, right? We've had 8 quizzes. I'm prepping a lecture for next week that I have. It's brand new, like it's all there, right? All new stuff. I'm doing the part of the job that's really well. I feel like it's not going well for you. And it's interesting, like if I went back to the system I had previous, like if I had just done, like the last time I taught multivariate, which was 2 years ago at this university, it was a hot mess. It was terrible, right? I can tell you that. I'm happy to say that. You can go find my slides and see what I did, and it was just, I'm not proud of it. So I feel like I've improved the pride, but I feel like you're not, the happiness of the students, where they were so happy with the terrible product that was before. All right, so maybe that's it. Maybe it's just like, yeah, Ben.
And on a high note,
Yeah.
while the homework was frustrating at the beginning of the year, just because getting me started, by the end of it, now that we've done 5,
Mhm.
I mean, I feel a lot more comfortable with R, and the homework I'm hoping to go back to in the future if I want to do it.
That's what I'm hoping too, yeah.
That stuff I feel like worked. Although it's frustrating at the beginning.
Oh gosh, yes, it's frustrating at the end too, because don't get me wrong, I get it, I get it. It's not. I wish that were much easier. Like I wish you could change your password. I wish you weren't like the login that you were because I couldn't add you to the list. Right? There's all sorts of things I could do better with it, right? But it's like, but yeah, it's frustrating. I hope that that's good. I hope that that helps. I hope that it got you to be a little more interactive with R, or with the material, and I think that wins, and then we come out ahead overall. So, for sure, yeah.
I'm gonna add to what you were saying too, that as a teacher, students are always gonna complain. But that
This is
doesn't
good to
mean
hear.
That doesn't mean that they're unhappy.
Okay, that's good.
You know?
That's good.
That-
Well, I care very much about you, even if you complain.
That when we are happy, we don't like run to your office for 2 hours and say, I am so happy.
No, you got it done. You get your life back,
We,
right?
we only go to your office when we're unhappy trying to figure it out. So
That's a good point.
just-
It is not a. It is, there's a missing data problem. Is what you're trying to tell me, right? So, okay, Caucasian and multivariate term. Okay, no, I get it. I get it. I can't be everybody's friend, and I can't make everybody happy, but I can. I do want you to be. If it's tough, I get it. It's hard. It was hard. It took me years to understand this as well. Years, not a class. Years, right? And I get it. But I hope it's been fair. I hope you understand the process I'm doing, even with the quizzes. I just, anything that you can do to help me get better at it for the next round, I'm happy to listen to. And yeah, I get it. I'm not perfect. I have lots of things I know I need to work on. There was a lecture in the middle I was really not proud of also, at least. And there's some of them I'm like, yeah, this is a great lecture. There's always better improvements, right? So this lecture, though, is one I've been promising a group of students, including Megan, since she came to grad school, which was at Nebraska years ago. Can I tell a little backstory? I'm going to tell you a little about Megan's life. I met Megan when she was looking to go to grad school, and she picked my wife and I at Nebraska to go do her PhD in quant psych at Nebraska. And we're like, cool, we're about to admit you, come out and see this university, but don't get too attached because we're leaving. But the whole time, I think even when you were there, I was talking about hating this, or doing it. So this lecture is a blend of, like everything in this class, the old with the new. I want to give you a little bit of the framework that still gets used, and then give you the modern version of it. And this was so relevant because just last week, in a comps defense for a program, a student in my program, I brought up things that were at the end of this lecture, and the other faculty in my program didn't understand them. Right? So this is where things start to differ, and this is why I want to give you material format. Now, as a point of reference, this isn't stuff that just got published 2 weeks ago. The stuff at the end here was published in 1971, based on stuff that started in 1940. Right? So this is still quite lengthy in age, but you don't hear about it when you take multivariate from the old way. And so I want to give you some of the old and some of the new to make this work. And then you're going to have homework that's awesome. Not really. There are no end of homework assignment questions, but I'll show you. So we're going to talk about principal components analysis, exploratory factor analysis, and then doing those types of analyses with confirmatory factor analysis, or CFA. And I put up here why I hate EFA. Hate's a strong word, but we'll go a step further. There's a statistical reason why I hate the way that EFA gets implemented. How's that sound? There's a bigger philosophical reason that will never be solved with the use of it. But I'm willing to at least deal with the latter part. The stat part I can't deal with. I'm like, I can see what it's doing and I don't like it. Not going to do it. Right? So there we go. So we're going to talk about methods for doing exploratory factor analysis. If you haven't heard this before, wait a slide. I've got more information on what exploratory factor analysis is, what its purpose is. There are principal components-based methods, which I say are terrible. There are maximum likelihood-based exploratory factor analysis methods, which are bad, but at least there's ML, right? Can we at least agree? Did you get ML in this class? Did you get that? Awesome, thank you. And then exploratory structural equation modeling, it shows up out there. Actually, I don't even cover that in here. M+ does it. What the hell's that, right? Bad. But then we're going to compare and contrast things. And we're going to talk about how to do exploratory analyses, if you must, with a confirmatory approach. Well, that brings up the logic of all this. So what is an exploratory analysis in the first place? An exploratory analysis attempts to discover the hidden structure of your data, right? It's like you collected all this data and you can't see what's underneath it, right? You've got to kind of like, shake it around, or, I don't know, like blow on it, or like rub a magic lamp, or I don't know what people do to it's like panning for gold, right? When I grew up in the Northern California, field trips where the gold rush happened, and we would seriously pan for gold, right? God, that was boring. You think math statistics is bad, right? But like, you pull up a bunch of sand and you're like, hey, I got structure in here, right? And that sounds great, right? You essentially go and collect data, and you submit data to this black box, or an R, which is whatever you want to use, and it tells you, hey, guess what you collected? I know, it's right here. I found it, right? It's kind of like you go to the mountains of Northern California, you take your gold pen, shove it in the dirt, get some water on it, and sure enough, there's gold, right? Turned out there were other things too, like fool's gold. That stuff sucked. That's like all I got as a kid, right? Anyway, that sounds great, but the problem is it doesn't work like that, right? You don't just collect data, submit it to an analysis, and it tells you what's in your data, right? Particularly where this gets used is with survey data or questionnaire data, right? You fill out a questionnaire, you have people go and write the items, or take the items, they diligently give you their data, and you throw it in the algorithm, and it tells you, hey, look at that, there's one factor behind these data, or there are two factors. What are the factors? Well, that was the thing you're intended to measure, right? If we were trying to measure self-esteem, we'd write items that were supposed to be about self-esteem, and then we'd submit it to this analysis, and it'd come back and say, hey, guess what? You measured self-esteem. Congrats. Right? That's what it's supposed to do. The reality of it is, statistically, that is impossible. Right? It's not likely to give you the right answer when you use it. So, from a statistical point of view, it's a really sketchy approach. But philosophically, it's also sketchy, right? So think about what we had to do in that rubric I just showed you. You're interested in studying self-esteem. And you write, let's say, 10 items to go study self-esteem, right? Or better yet, here. I'm going to just introduce homework right now. Another way to make you feel bad. By the way, homework is due 2 weeks again from today, which is the week of finals. Next week's office hours is on Thursday instead of Tuesday. But then there will be an office hours on Tuesday of the week of finals. So I'll send an email with this information when I go out as well. So again, the same structure that we've had the whole class. So this homework assignment, you can't see it. This is actual data. So I taught a workshop last year in Boulder, and I had a professor in my class, and she was interested in doing some type of survey of people's beliefs in conspiracy theories. Right? So she created 10 items to go and measure people's beliefs in conspiracy theories. So here are the 10 items, like President Barack Obama was not really born in the United States. He does not have an authentic Hawaiian birth certificate. Or government officials are covertly building a 12-lane NAFTA superhighway that runs from Mexico to Canada through America's heartland, right? These are all items that people had to go and circle strongly disagree to strongly agree with somewhere on that scale. And if you're like me, you get this and you're like, oh, I'm going to strongly agree with all of them. I'm going to pretend I'm a nut job, right? But you think about it. This person at my workshop, there's a typo. Damn it. Do so much better. Anyway, proofreading's not my strong suit. She clearly had an idea as to what to build into this survey. There are 10 items. The score from this test, however you want to score it, either adding it up or doing other fancy models, is supposed to represent beliefs in conspiracies, right? So people who score really high on this are agreeing with all of these, and their belief is really strong, right? So if you were to believe in the logic of exploratory analyses, if you didn't have the methods that I'm going to talk about at the end of the lecture, you would take this and blindly submit it to a computer with the hope that the computer said, yeah, you're measuring one thing. It's beliefs in conspiracy, right? So where that breaks down, the part at the end is where you go and say, okay, yeah, I built this for a reason. Is there one structure? Is there one factor behind it, right? That's the confirmatory approach. The exploratory approach is, I don't know how many factors I have. There could be 1, there could be 6. I don't know. The confirmatory approach is there one? Right? It's a hypothesis test. I hypothesize there's one factor. Right? So that's the difference in the approaches. So to be doing exploratory factor analysis when you created your survey for a very, very good reason is crazy, right? Because the exploratory factor analysis starts off by saying, hey, how many factors do you have? Yeah, it doesn't matter that you actually know that you created one. You're trying to create one. You're trying to say, wait, I don't know. Like, to me, it's like saying this. When would you ever, like, it's like, what's the example I like to give? If you ever seen there's a show called Storage Wars, or used to be. You know what I'm talking about? What's it about?
That's exactly what it sounds like. People that have abandoned their storage containers for a variety of reasons. People kind of swoop in like vultures and try to get bids on the
You
stuff that's in
can
it.
bid on a storage locker full of somebody else's stuff when they don't pay their bill, right? But you can't go in it and see what's in it before you bid. So if you're bidding on it, and all of a sudden you win, and they open the locker, and sure enough, there's a USB drive. And you're like, oh, sweet. I got a USB drive, and you plug it into your computer with a good virus scanner on it, don't worry, right? And you find there's an SPSS file on there. I'll just say SPSS, because that's the people who run exploratory factor analysis. They'll use SPSS. Anyway, sorry. But the problem is the coded area for where the variable names is, they're all jumbled. It's like just random numbers, like or x1 through x20. So you have no idea what the variables are. You have no idea how you collected them. All right, I get it. Now you want to do exploratory factor analysis. I don't know what this is. That's great. I just collect these data randomly. And I'm going to go figure out what's in it. Totally cool. Totally legit. But when you build a survey on purpose, you don't need to start there. You can say, hey, I built it to be like this. Does it fit? Does model fit? Right? We've all talked about model fit in here. So that's kind of my beef with the theory of exploratory. Yeah.
Back on the homework real quick.
Yeah.
There's no syntax and you spelled Obama's name wrong.
Oh, you're kidding me.
Not kidding you.
Gosh darn it. Oh my goodness. My apologies. I will fix that. There will be syntax. So, my problem with it statistically is the statistics behind the exploratory analysis can give you misleading results. The conceptual issue with it is still an issue. But there's times where you might be, actually here, let me go with the statistics real quick. So why would they give you misleading results? Well, number one, a big one is if your data don't meet the assumptions of what you're using the analysis for. Right? In ML EFA, and we all agree we love ML, that assumption is multivariate normal. So you have data that are Likert scale like these, probably not going to work. Right? Data that have quirks that are idiosyncratic to the sample selected. The data that I gave you is actual live raw data from people, undergraduate students at Oklahoma State. Pretty amazing, right? Each of you has a different resampled version of it, right? So there were 177 cases. I drew 177 at random with replacement for your data set, right? So as a bootstrap, we call that. And wouldn't you believe, I watched as it took an hour to generate your homework answers, and I had it spit out how many factors for each one of you should find. And you wouldn't believe the consistency with it which it had. It had none. Like it was a uniform distribution of factors that were in the data it said. Right? So think of it that way, right? If I did this bootstrap resampling, sometimes some of you have one factor in your analysis. Some of you have 6. Right? And it's essentially a roughly equal proportion of you have 1 to 6 factors in your data. And this is live, real data. I didn't generate this myself. It's just to show you. So what I'm talking about there is each little subsample, each little bootstrap resample I give you of your data is a snapshot of the real thing that's going on, and it's not going to be the same for each of you. You may have outliers that are extreme or cases that are extreme, particularly if you have people who are like me responding to your survey, right? I'm like putting 5s down on all these, yeehaw, conspiracy, right? Or here's the last one. This is the stat version. The constraints in the analysis are implausible. Nobody likes to talk about constraining anything, but let's be real. Last week, compound symmetry put constraints on the covariance. Right? We said all the variances were equal, all the covariances equal. Whether or not that was actually the case, we don't know, but we're just going to lock those in and run with it. In the exploratory factor analysis, ML version, there's also a set of constraints. But what they happen to be, nobody talks about. Talk really quietly about. Right? Like if you go to SAS's user guide, which SAS's proc factor, and their user guide is wonderful if you're into statistics. Like it tells you how each method is done and whatnot in the citation score. It's a really good archive of stuff to do. It says, yeah, the constraints are based on Lawley and Maxwell 1971. All right, that's it. Doesn't actually put them in. So you have to go and find them. I'll tell you what they are. I actually just checked out Lawley and Maxwell's 1971 book just to make sure I'm doing this the way they wanted to see if it's motivation they have. Didn't quite get there yet, but anyway. So I will make you the case that the stat argument for it is enough to say no. Right? The conceptual argument's pretty strong, but I will say that there are times where exploratory analyses are needed. And if you think about it, particularly when you get into measurement models of these types of factor analysis or building surveys, there's never just one model that you run. Right? It's never the case where you just go, yes, I have one factor, and I'm going to run one. I guess if you're an IRT, maybe. I don't know. Large-scale testing, maybe. I don't know. But what happens is, generally speaking, you take your one factor, you see if it fits. And more often than not, it doesn't fit. So you tinker around with it. Either you add another factor to it, or you drop a few items that weren't quite doing well with the data, or so forth. And then you try it again. And you see if it fits. And if it doesn't fit, you still do some more tinkering, and you still do this process. And that process, from start to finish, is a bit exploratory. Right? You're sort of saying, what if I try this? What if I try this? What if I try this? You're exploring it, but you're doing it in a way where particularly some of these issues, statistics, especially the constraints, are known to you. So what I'll say is that generally speaking, most exploratory analyses, the philosophy of it is pretty terrible, but doing it in sort of a guided and regimented way is what we do. It still may lead to a inconsistency in results. You may still have those issues. If you did bootstrap resampling, you might see a number of things, but at least it won't be because of some of these cases up here. So, okay. Finally, as a journal associate editor and other places, I used to serve on the editorial board of School Psychology Quarterly. How about that, my school psych friends? I'm a school psychologist because my friend Randy Camphouse, I worked with him and he put me on the journal. How nice is that? But anyway, I felt like they allowed me to get, I was where the papers went to die because they would send me a paper they didn't want, pretty sure they didn't want to publish. And my opinion of it would be, the paper would read like this. I believe there are 4 factors in self-esteem. So I created a 4-factor survey. I collected data on the 4-factor survey, and look, I did an exploratory factor analysis that said I have no idea how many factors are, and it sure enough, it came back with 4, right? That to me is crazy because if you know you had 4 to begin with, start with the confirmatory model and move forward with it. So, anyway, how we doing? I'm hating, but in a different direction. I'm trying to motivate why I do this. My REM students, be critical on this. What am I missing out here? Where's your questions? My REM students, my program. I don't possess anybody. I have 2 children, but they're not possessive. No, I advise people, not a possession. Sometimes I advise them to go get other opinions, but not asking you to leave. Anybody have questions on this? Okay, let me lead off with the old. All right, to get to the old, though, we need to know a little bit more matrix algebra. Just what you wanted to hear. But I'm going to hit the accelerator button on this. Questions? Did I see a question? Okay. Here's an example. I brought this data out a long time ago for the matrix algebra lecture. I have 1,000 students. They pretended to take the SAT math and verbal. Here's the means, standard deviations, and the correlations between those. There was a topic, I don't think we talked about this. I think we did. The matrix trace. Do you remember hearing about the trace of a matrix? That's good. It's brief. It's going to be brief. The trace is brief because it's somewhat understandable relative to some of the other things. So here's a correlation matrix. The trace is the sum of the diagonal elements. Right, so for every correlation matrix, the trace will be an integer because the diagonals should all be 1. And we all like that. So there'll be a trace of 2 here for that matrix. For a covariance matrix, it'll be a different number altogether. Why that becomes important is to do principal components analysis. What we are extracting from the computer, extracting, I hate that word. When we're doing factor analysis, this exploratory, we're extracting. It's like we're pulling teeth out of the analysis, right? We're dentists pulling those wisdom teeth. That's another term for you. Make everybody feel better, all right? That's the word they use. They extract factors. And each factor that you've extracted, you want to describe how much variance in the data it accounts for. And so for each factor, there's a number that summarizes how much variance there is. Now, I'm saying factor, but it turns out in principal components, they're really more mathematical. They're not really factors. We'll call them components. But that total sample variance that you're trying, the target you're looking for, is equal to the trace, right? So if you come up with a factor solution and it explains 90% of the variance, what that 90% of is the trace, right? The variance that comes from the factors represents the numerator, and this is the denominator in that itself. Weird, huh? In your homework, you're going to have to use principal components analysis to figure out number of factors. And the number of factors you're going to look for is the number that gets you above 70% of variance explained, right? So you don't have to do a trace. It's done for you. It's all taken care of, but that's where it's coming. Now, we did talk about determinants. A matrix determinant is a total sample variance. Shows up from time to time. This helps us to tell whether or not our stuff is positive or non-positive definite. That's just, I usually pull that together when I talk about traces, but I don't really need to talk about that here as much, although I really love that generalized sample variance. That's the thing I want to make happen, that R square across all your variables. It's not going to happen. Now here's a new one. If you have a square matrix, say a square matrix lambda. Lambda is said to be orthogonal if the following thing happens. Actually, it doesn't even have to be a square matrix for this to be true. Square matrix gives us these two before and after the equals, pre and post multiplied. We'll go with this. If the matrix times itself transpose, if it's orthogonal, it will be equal to the case where you take the transpose and multiply it by itself, and all of that will be equal to the identity matrix. Remember the identity matrix? Identity matrix had ones down the diagonal, zeros in the off diagonal. So an orthogonal matrix, and actually this is actually a little bit more stricter. This is an orthonormal matrix. The orthogonality, if you remember the vector angles, vectors are said to be orthogonal, and this is all I'm going to say with it, when there's a 90-degree angle between them. And remember, the vector angles relate to correlations. It's like saying there's zero correlation between the two variables they represent. This thing right here is going to be like our covariance matrix itself. And so when it's zeros in the off diagonal, it's like saying all these variables are orthogonal. So if lambda had our data in it, in this case it's not really data, but if we could do that with data, we'd see that these would be variables that had zero covariance between them, or, and furthermore, a diagonal or a variance of 1. So orthogonal gives you the 0 and the off diagonal. The diagonal elements here, being 1, represent vectors that are normalized. That this really could be thought of for matrix algebra before we talked about dot products and that being related to vector. Well, let's just talk about that. Never mind. Point is, this thing represents, if you think about what this is doing, this vector multiplication, yes, I will go back to dot product. The dot product between any column of this and any row of the other one, right? If you take the same column number that is row number, that's the dot product of a vector with itself, right? So that would be like the sum of the squared elements, which is like the length squared. When that thing is 1, like it needs to be for the diagonal of this, that's like saying our vectors all have the same length, unit length, right? Why is that important? Well, in principal components analysis, there is no one solution to the analysis. There's an infinite number. Right? So when we go and do PCA, we try to figure out how many factors to extract. The things it gives us can be almost any number. But if we go and say, no, the vectors that you're giving us, if we fix the length of them to 1, then we can have a solution that is sort of the same for everybody. So that's kind of the distinction we throw in. It's an odd thing. It's essentially a scaling constant. Anyway, quick. If that wasn't fun, this really is. Eigenvalues and eigenvectors. For every square symmetric matrix, and I'm going to limit my conversation to square and symmetric because this method of principal components is really a method of trying to figure out the eigenvalues and eigenvectors from either a covariance or correlation matrix, right? So you get your data, you form a correlation or covariance, and you do this thing to it. But the definition of these things, actually a little personal history here, this is what got me into grad school in quant psych, and quant methods in the first place, because I saw this as an undergrad, and I used SPSS. And there was something called an eigenvalue in my output. And I went to my professor, my junior year of undergrad, and I said, hey, what's an eigenvalue? It's like, no clue. Go take matrix algebra. So I went to go take matrix algebra. And the first day I went there, I said to the professor, hey, what's an eigenvalue? And he's like, oh, an eigenvalue. Yeah, that's a scalar that does the same thing as a matrix. Right? Essentially, it's saying, oh, yeah, if you're going to multiply, I can take this vector E, and I can do the same thing a matrix does when it multiplies it by multiplying it by a scalar. Doesn't tell me anything, right? Great, so now I got to go to grad school, and I'll end up teaching multivariate and teaching this stuff. Actually, I'm really happy. This is a fun topic for me to teach. But really, the way you can think of eigenvalues and eigenvectors, these are things that are crazy, but they're properties of the matrix itself, properties of a covariance matrix. And every square symmetric matrix has a set of them. In fact, for every element of this matrix, so if this is a correlation matrix, there will be an equal number of, so every, the rows and columns are the same, the number of variables you have. There's as many eigenvalues as there are variables in your correlation matrix. And there is as many eigenvectors as there are variables in your correlation matrix. The eigenvalue is called lambda. That is its own little thing. The eigenvector, we usually use E to represent it. And so each eigenvector gets paired with an eigenvalue. Right? So it's like saying if I have two variables, I'm going to come up with two eigenvalues. Each eigenvalue will have its same associated eigenvector. That's it to principal components now. So we throw a whole bunch of other stuff on top of it. That's it. That is it in a nutshell. I'm going to show you that in just a second. But in that process, to make this a unique solution, what we end up doing is taking the eigenvectors. These are just, I haven't defined these more than just, these are just vectors. And we make them so that their length is 1. Right? Not only is their length 1, they are orthogonal. Right? So if we took all of the eigenvectors, we multiplied them with any other, we have two here. We have eigenvector 1, eigenvector 2 for our two variable analysis. If we did the dot product of them, the dot product would be 0. If we did a dot product of eigenvector 1 with eigenvector 1, it would give us a value of 1. Right, so it meets that orthonormal or orthogonal matrix that we saw from the previous slide. It's a lot to digest. Let's just talk about this in numbers. What I did to figure this out is I took the correlation matrix of our data. Right? So I created an SAT correlation matrix. This is a 2x2 matrix. And I went into R and I used the function eigen. I gave it the correlation matrix, and I told it it was a symmetric matrix. I don't have to tell it symmetric, but that speeds the process up. Out popped the following sets of numbers. There are two eigenvalues, 1.78 and 0.22, and two eigenvectors. And in the principal components analysis, the eigenvalues, starting with eigenvectors, the eigenvector itself is thought to represent the factor loadings of a factor. Well, they're not factor loadings, and it's not a factor. This is a recombination of data. But if you go to your data, right, if you start with the data that, in our case, because I'm using a correlation matrix, so you start with the z-score of every piece of data, and you multiply each person's z-score by its respective eigen element of this eigenvector and sum them together. you get what's called a component score for that person. Weird? With me? So think of it this way. I have my SAT data. There's SAT math, SAT verbal, and I've made z-scores out. Okay? So for each person, I go take 0.71 and multiply it by SAT verbal. And add that to 0.71 times SAT math. And now I have a brand new composite score for each person, which is 0.71 times verbal plus 0.71 times math. That new composite score is called a principal component. In the twisted world that is factor analysis from 50 to 60 years ago, they would call that a factor. It's a component. All right, so if you think about what I've just done, for every person in my data, I've created a brand new variable, E, that's a combination of both math and verbal SAT. Right? And if we're going to use, the reason we use this typically, principal components, why we still use it, where it does seem a little bit more justified, is if this wasn't just two variables, if I have 350 and I want to boil them down into a summary number, this would be one way to do so. Instead of using all the variables in my data, I could use this new component itself. With me? So, when I do that, if I want to know what the variance of that new component is, I can find it exactly from this output. The variance of that new component is given by the corresponding eigenvalue. So if I go and take my data and take SAT math, SAT verbal, say, you know what, I don't want to use both of those variables. That's too many for me. I'm just going to go and use one variable. So I weight each by 0.71, and I can create this new variable. I can tell you ahead of time the new variable will have variance 1.78. That's what an eigenvalue does. How are we doing with that? It's weird. Weird stuff. It took class upon class to be able to describe this. Yeah, Ben.
Explain again. So why is 1 the standard? It's like 1.1. Like 1 of the variance compared to 0.99 or something like that. Isn't 1 the standard?
So how many variables to extract? Yeah, people like to say a variance of 1. What a variance of 1 represents is if you were to create a brand new variable out of this kind of combination that we have here, you'll have more variation in that variable than any one variable in the data set on average. That's what it's saying. Right? Because if you think of this, the correlation matrix, each variable standardized has variance of 1. Right? But when you pool them together, are you getting more variation out of it? That's what you're looking for here, right? So the more correlated they would be, the higher that variance of what component might be. The standard, though, is kind of bunk anyway. It's just made up. Yeah. So, you ready to have your mind blown a little bit more? This can get even more fun. So that eigenvalue, eigenvector thing that you see with this, this equation here, by the way, if you factor the e's onto one side and you move the other terms to another side, factor-like terms and so forth, what you get is what we call the characteristic root of this, and you can find, or the characteristic equation, if you find the roots of the equation, that happens to be the solution that gives you eigenvalues and eigenvectors. And there was a time in my life, I'm old enough to say I did that by hand several times. It's not fun. I'm not making you do that. When I was in grad school in multivariate, we had to do it by hand. That's how old I am, right? Okay, could be worse, right? But here, this is eigenvalues and eigenvectors. That covariance matrix that we started with, or the correlation matrix that we started with, sigma, we can actually get back to through successive approximation. So, for instance, if we took the first eigenvalue, lambda 1, multiplied that by eigenvector 1 times eigenvector 1 transpose. So here's the matrix for it. We get this matrix 0.89 right there. All right, that's a little weird. It doesn't look like a correlation matrix. But if I take this matrix and add to it the same thing, but for the second eigenvector and the second eigenvalue, right, all the way down here, I end up with the original correlation matrix. I get 100% back. So what we're doing with this is something that we call the spectral decomposition. We can take a matrix, and in this case a square symmetric matrix, and do this process to it where we get eigenvalues and eigenvectors, and for each component that we use, we're sort of approximating that matrix successively. we get closer and closer and closer to full solution. So if you think about data science, I love that term, data science. When we do eigenvalues and eigenvectors, what they're doing essentially is trying to find a compacted version of a covariance or correlation matrix when you extract. Right? So if you only take one, it's like saying, oh, my data would look like this if I put them on. If I took another, it would look like that. In the early days of compression algorithms to create images and video and so forth, this was how you would compress data. Right? If you think of an image, a bitmap, each pixel in a bitmap has a vector of information for it, right? In the old days, it was red, green, blue values, right? Back in the old monitors. So there is this actual crazy three-dimensional box with volume of stuff. And if we're doing a similar analysis with it, we could do a similar spectral decomposition and take a bitmap, reduce its size in terms of kilobytes, because not every number needs to be represented, into a smaller thing, and yet still get fairly good representation to make that image look about the same. Right? So if we took a rank 1 of, what do we call this, a rank 1 approximation, if we did this on that three-dimensional box, we'd get the picture. We'd essentially get a good glimpse of the picture. We'd lose some of the resolution in it, but we'd still get an accurate picture glimpse. So a lot of this methodology that you see here can be useful in, a lot of times in SPSS when I was younger, it used to be called dimension reduction, right? Sort of reduce the size of the data. We won't go from having, in this case, 2 variables to 1, but if you had a bitmap, it'd be thousands and thousands of pieces of information to a smaller set. Questions? Don't take my word for it. R will do it for you too. Weird? So that's the math behind it. Let's move forward to what we do. Actually, by the way, another neat thing about the eigenvalues, if you noticed before, the sum of the eigenvalues equals the trace, the covariance, the matrix that you got them from. The product of the eigenvalues gives you the determinant. And if you're into figuring out whether things need to be non-positive definite, remember that term? Or positive definite? If all of the eigenvalues are greater than 0, your matrix is positive definite. If one or more are equal to 0, it's positive semi-definite, meaning it's right on the boundary of being inverted. And if any are negative, it means it's non-positive definite, not invertible. So there are catches that you can do for matrices there as well. And if you're into programming, if you're into estimating, if you're into that stuff, I'm telling this to you kids in REMS, that is a useful trick to know, or maybe not just REMS, everybody who's into that, but I'm especially pointed at my program students because that's where I reside. There are always catches in statistics that you can do to figure out how to keep a matrix non-positive definite or positive definite to make sure it's invertible, and this is one of them. Okay, so principal components analysis is all of that, but it's applied to data. It's a method for re-expressing the covariance, or often the correlation matrix between a set of variables. And what this re-expression gives us is a new set of variables, these component scores themselves. Those new sets of variables is what people call factors. I don't like to call them that because they're not factors, but that is what people call them. It has two objections. I have two objections. It has two objectives. It wants to reduce your data. Right? If you've got 350 variables, I don't know why that's the number I'm pulling out of my hat this week, but 350, and you want to go down to 3, it's fine. Actually, I'll give you an example where this is used. In large-scale assessments, like National Assessment of Educational Progress, there's a test we give out every 4 years, people in 4th grade, 8th grade, 12th grade, but we don't give it out to everyone in the country. We have this spiral sample design to try to compare county by county within a state or state by state, or groups within a state, or groups within the nation. So we could say, for instance, that Kansas is either better or worse than Alabama, let's say, at whatever subject area, math. In that, we oversample certain populations because we're interested in them, or they're very hard to get at random from a sample. One of those populations would be the native population in the United States. And to weight our analysis, what we have to do if we don't go, and when we ever do any analysis with the data afterwards, if we don't go and re-represent the sample that represents the United States demographics, then we're going to bias our parameters in favor of the oversampled populations. Our parameters will look more like it would be in certain populations. And if there's no difference in populations on the parameters, that's fine, but oftentimes there will be, particularly when the variable of interest is achievement in academics. Right? There's big differences in demographics and achievement in academics. So I tell you that story because they do collect some 300 variables of demographics, and how they create a weight with it is through principal components. They use a principal components analysis to get a weight that represents some amount of information on demographics for the student or the surrounding area or all the places where the test was administered. And they use that in the analysis to weight the data. So this is one reason for it. Oftentimes, you can't weight by more than 1 or 2 terms in a weighted variable analysis, and this is one that fixes it. So, the other thing that we want to do with data is to interpret it. So we go, once we figure out how many components are in our data, we want to interpret each one. What does each mean, right? And the way we do that is to figure out which variables contribute most to each component. So the goal is to find a set of k principal components, which are these composite variables, these linear combinations of your original data, such that it's smaller than the original size of the data in terms of number of variables. So k is much smaller than v usually in this notation. And it accounts for nearly all of the total amount of variance already there. So you're basically saying, I've got 300 things. I'm going to reduce it into, let's say, 3. But I want those 3 things to be able to account for 70% of the variance of all of my 300. Right? Can I come up with 3 things that do the job of 300? That's what this is essentially saying. Pretty cool. Can it be done? No. It's too good to be true. But no. Yes, people do it all the time, actually. So if you can accomplish these 2 goals, then that smaller set of variables, the principal components that we call, contains almost as much information as the original variables, and that means we will now forget the original data and focus only on our principal components in any subsequent analysis that we move forward. Who works with Joe Weir? He does this with force plate data. Collect a lot of data on, the electrical signals that comes from muscle, right? But there's way too much data. And so how do you go and synthesize it? Well, if we took several components of the data, we might be able to describe certain forms, general average trends. And so that's one way forward. Tons of data on any one replication of an experiment that you might be running. ERP data. So people like Lauren, you've got your network, not neural network, your network of recording sites on someone's skull, sorry for the terms, and you've got too much data, right? What do you do with it? Well, you have to reduce it somehow. Katrina.
You mentioned earlier, and then again, the 70%. Is that like a rule of thumb?
No.
Or is that like...
That's the thing. This has gone on for so many years. The rules of thumb are so idiosyncratic to almost like whomever is using it. I can tell you 70. Someone else can tell you 90.
So that's just your number.
That's my number for this homework assignment. And actually, it's motivated in this, if I'm being completely honest, it's motivated to make sure that we at least had some solutions for the homework that you could report on. Because I have this random process to assign data sets, and I wanted to make sure that some of you wouldn't be like, yeah, I'm interpreting 9 things. Right? We don't want that to happen. Yeah, I would tell you, from my point of view, more is better, but then again, where you get to more is hard to tell. So we have to answer these 2 questions by doing things sequentially. We first answer how many components of these new variables are needed to adequately represent the data. Like Katrina asked, that's a fuzzy concept. Adequate varies. There's a lot of subjectivity in this process. Then after that, once you've figured that out, then for each variable, what does it mean? What does it mean? What does this component mean? That also is fuzzy. And that's why in the homework you'll see there's no results section. I guess there's one question down there, but I actually give you no points for it because there's one option. It says homework is over. I am happy. Right? That's it. You have no other choice but be happy when you click that, okay? I was making sure that you all got that one right, okay? Better yet, I should have said your instructor is. Now, we're all happy, right? It's tough. It's tough stuff. Okay, so a lot of times people pitch it as principal components often reveals these relationships between variables that were not previously suspected. So for instance, if you have this new component, maybe you have 4 components. And on the second component, variable 30 and variable 71 are really prominent in this weighting. Those 2 variables now are thought to be related to this thing, whatever it happens to be. You may not have seen that in a correlation matrix before. Now, the pragmatic point of me is that the PCA, principal components analysis, is really more of a means to an end rather than an end. Right? I like to see, I don't mind the way it reduces dimensionality. If I'm going to do a weighted variable analysis and I've got 300 demographic variables, I'll do this too. I don't care what the component means though. I just want it to represent the data in a way that's somewhat easy to use somewhere else. So we often see people do that. They take PCA and they use the components and other techniques like clustering or linear models or however else. And a lot of times, though, principal components gets intermixed with exploratory factor analysis. The difference is, it's very interesting, exploratory factor analysis starts in history about the same time that principal components starts in the 1930s. The difference is, though, that what we're putting into this, all of them rely on the spectral decomposition to give us our covariance matrix back. What the form of the diagonal of the covariance matrix is differs by technique. But what really happens, historically, is that principal components was a rudimentary tool to give you a factor analytic solution in the late 1930s, early 1940s. Because we didn't have computers, and maximum likelihood theory for factor analysis started with Lawley in 1940 was the earliest paper I saw. But you weren't going to get that. In fact, the REMS program students, you wouldn't be working for CETE, or you may be working for CETE when you were there before as a student in the 1940s, but your job wouldn't be writing items or doing analyses or playing with Excel. I don't know what you do. Your job would be to literally do principal components on some covariance matrix, but to do it by hand. And your solution may take you 2 or 3 years to actually achieve, right? That is how it was. And so to do that, you could get a result with PCA back then. Whereas maximum likelihood, you wouldn't get a result. So the unfortunate part of that is that PCA was the first that came out to do this type of work for factor analysis, but it needs to stop because it's not factor analysis. All the types of factor analysis that shows up, everything in the drop-down menu in SPSS with the exception of maximum likelihood is based on PCA and some shortcut to try to give you what ML is trying to give you. So stop it. That's what I'll tell you. Stop it. Please make it stop. Right? It's not factor analysis. It's not doing what you want it to do. And we're going to talk about factor analysis in a bit. But let's take a break. 10 minutes. And I'll go and rip on factor analysis next. Hate.